Hello, everyone, and welcome to another wonderful day of chemistry. So previously, we've been talking about how we can make use of equilibrium constants to determine the eventual concentrations of any number of reactions or species. However, this time I want to go ahead and focus in on how we can actually get the equilibrium constants we want. Most of the time, you're going to go ahead and obtain an equilibrium constant by looking somewhere in a table or in a book. However, sometimes they're not in the form you'd actually like. So one of the classic problems is the provided equilibrium constant isn't going to be exactly how you want it. So the simplest of which is you've got the reverse reaction. So let's say I'm looking at I want to try and figure out how readily nitrogen and oxygen combine to form nitric oxide. Unfortunately, the value in the table is going to be the reverse one, so the decomposition of nitric oxide. So I have to figure out how to relate these two equilibrium constants. Now, it turns out you can go ahead and obtain the equilibrium constant for a reverse reaction simply by taking the inverse of the forward reaction. And this makes sense to a certain extent. I know that this reaction is going to be very favorable, large K. So that means that the reverse reaction written here is going to be unfavorable. It'll have a very small K. And lo and behold, you can get that by taking the inverse. So if I take 1 over that very big number, I end up with a very small number. And this is a good way of guaranteeing that a favorable forward reaction has an unfavorable reverse reaction. And if you want to go ahead and prove this, feel free to write out the equilibrium expressions for both of these, and you'll find that they're the inverse of each other. However, a lot of times our reactions are only going to differ by a coefficient. So again, let's say I'm looking at the decomposition of nitrous oxide. Now, in this case, I start with 2 moles of NO. However, I might be interested in a amount of energy or the favorability per mole. So at this point, I want to divide this reaction by 2, which is the same thing as multiplying the whole reaction by 1/2. So what I can do is use that coefficient of 1/2. And if I multiply the reaction by a coefficient of 1/2, that's going to be the same thing as taking the previous equilibrium constant and raising it to that power. So this reaction is the same as this reaction times 1/2. So it means it's the same as this equilibrium constant raised to the 1/2 power, also known as the square root. So to get our new equilibrium constant, we can take the square root of the old one. And you'll note that this one seems a little less intuitive because this looks very favorable and this looks less favorable. But we can actually validate why this kind of happens by looking at the two equilibrium expressions. So if I'm looking at the second reaction, I'd be looking at the concentration of products, so in this case, in terms of pressure, each raised their coefficient power. So pressure of nitrogen to the 1/2, pressure of oxygen to the 1/2 over the pressure of nitrous oxide. Well, that's going to be the same thing as the equilibrium expression for my first reaction with the whole thing raised to the 1/2 power. And this does illustrate one of the things you have to watch out for when looking at equilibrium constant values, is that how much of that equilibrium constant is just the fact I'm consuming or generating a lot of products. So if I have a reaction that is very favorable, if I have it happening multiple times, it's going to become more favorable. And in contrast, if I have an unfavorable reaction occurring multiple times, it's going to increasingly become unfavorable. Now, the last major manipulation we have is if I'm trying to combine 2 known reactions to make a third reaction. So let's go ahead and say I want to combine the reaction of nitrogen and oxygen to make nitrous oxide with N2O breaking apart into nitrogen and oxygen. So if I combine these 2 reactions, we're going to note that the 2 nitrogens end up canceling out, and I cancel out 1/2 of the oxygen. And this generates this third reaction. Well, it turns out I can get my third equilibrium constant simply by multiplying the previous 2. So again, if we can think about this in terms of products over reactants, what we've done is just essentially canceled out everything. So it will be the same thing as multiplying these 2 equilibrium expressions. And that is actually a good practice to illustrate. So if I multiply these 2 values, what we end up getting is this third value of an unfavorable reaction. And this makes sense if we took a look at it. I take one very, very unfavorable reaction, combine it with one favorable reaction, and I end up with one mildly unfavorable reaction. So hopefully this all cognitively kind of makes sense. However, one of the things we tend to see the most frequently in chemistry is you aren't just going to be combining one or two reactions with one or two of these rules. You may have to be combining multiple reactions with all of these rules together to generate another reaction. So, for example, let's go ahead and take a look at combining 3 reactions to generate a fourth. So I want to figure out the equilibrium constant for combining nitrogen, oxygen, and chlorine to make NaCl. So in order to do this, we have to essentially first make NO2, which can then react with chlorine to make NO2Cl. This NO2Cl can then release a little bit of oxygen to make the desired species. So, all right, let's go ahead and figure this out. The first thing is I'm going to want to generate this as a product, which means I want K3, but it's in the wrong direction. So I'm going to need to take the inverse of it. So raise it to the -1 power, except for I want 2 moles of NaCl. I only have 1 here. So I've got to raise it to the -2 power. Then I'm going to need to get that NO2Cl from somewhere. Well, that works from this reaction as written, but I'm going to need to. So I've got to multiply, I've got to raise this to the 2nd power as well. But I need to get that NO2 somewhere. So I start with my first reaction and raise it to the 2nd power. Now I leave it as an exercise to prove that all of these cancel out. But essentially, if you multiply this one by 2, this one by 2, and flip this one and multiply by 2, combine all these together, you'll get my net combined reaction, which means I can get the equilibrium constant by taking the square of the first one, the square of the second one, and the inverse square of the third one. Or multiply the square of the first two, divide by the square of the third. If you do this, we end up with a net unfavorable reaction, which makes sense because a lot of this reaction is going to be dominated by 2 unfavorable forward reactions, and then we have to flip our only favorable reaction. So again, this should cognitively make sense, and always double check to make sure that your value agrees with what went into it. So this brings us to the end of looking at general equilibrium reactions. From here on, we're going to spend the next several chapters at looking at specific types of equilibrium systems. Next up, time to look at some acid-base chemistry. Until then, take care.